On behalf of U Alberta Geotechnical Center and USCGS Student Chapter, thank you very much for being here, and thank you, Dr. Yinghui Tian, for accepting our invitation and being here to present on the very interesting topic. At first, I will just go through his bio and through his abstract, then I will welcome Professor Tian. Professor Yinghui Tian is a Fellow of Engineers Australia and an ARC Future Fellow at the Department of Infrastructure Engineering, University of Melbourne. He specializes in offshore geotechnics with a current research focus on foundation systems for offshore renewable energy. Professor Tian is the recipient of the Institution of Civil Engineers David Hislop in 2017. He has authored over 200 publications, including journal papers, conference papers, book chapters, and technical reports. And today he's going to speak the topic offshore foundation solutions to support renewable development, applying helical anchors for offshore wind. His short summary of the speak goes like this. As the global demand for renewable energy continues to increase, offshore wind farms are emerging as a pivotal solution to meet sustainable energy targets. This seminar explores innovative foundation technologies that are economical to develop offshore renewable infrastructure, with a particular focus on helical anchors. Helical anchors offer several compelling advantages for offshore wind turbine foundations, including ease of installation, potential for reuse, and minimal environmental disturbance. The seminar will present recent research advancements aimed at improving the performance, scalability, and resilience of helical anchor system in offshore environments, highlighting their role in supporting the future of renewable energy. Okay, join me on welcoming Professor Tian over here, and Dr. Tian, the floor is yours. Thank you very much.
Thank you.
Just a minute.
Yeah.
Just a minute. No.
It's here already.
Okay.
Click here, and then the screen. That's fine. Yeah.
Yeah.
I'm just seeing the
Sorry. On Zoom.
Can you see this? Oh, I think we better share a screen rather than the file. Please reshare and yeah, stop sharing. Share the screen. Maybe easier. The screen.
Screen?
Yep, yeah. This one.
Screen, then go to see.
So the other one. Oh, I just
always technical difficulties.
oh.
Maybe I can just close. Is this one, maybe you have opened this one?
I don't need.
No?
There you go.
Yeah.
Perfect.
Yeah, all good?
Okay.
All good. Thank you. Thank you for the introduction. Morning, everyone. Really good pleasure to come over here to give this presentation. So I got to know Professor Deng quite a few years ago, and I've been in touch for many years. Eventually, very glad to have the opportunity to come over here. So today I'm going to talk about offshore foundation solutions to support renewable development, especially a focus on applying helical anchors for offshore wind. Professor Deng and group here is you are the experts on this, actually on this topic. My name is Yinghui Tian, just introduced. I'm from the University of Melbourne, So before I start the technical presentation, give you a little bit background about University of Melbourne. So University of Melbourne was established in 1853, the second oldest university in Australia, and ranked #1 in Australia constantly. And we're really lucky in recent years, the QS ranking did really well. We are 13th in the world, so it's really lucky. University of Melbourne quite proud of its leadership in academic activities, research, teaching. We have a quite big group, alumni group, doing really well in politics, science, engineering, and business. We are the second largest group, alumni group from among the Fortune 2000 company CEOs. We're quite proud of that. So you can see this picture. It's one corner of our campus. So the typical Australian sandstone building, old campus. But in the same time, we're building a new campus in the coming years. So if you know Melbourne, there's a river, Yarra River, that crosses the river, which was fisherman band. We have a land and going to build a new campus. Several years later, the faculty, engineering faculty, gonna move to the new campus. So I'm working at the Faculty of Engineering and Information Technology called FIT. In total, we have about 500. In Australia, we call Tian academic staff, the same as Canada, the tenure position. And we have 160 professional staff, including admin and lab technicians, and also postdocs. In this faculty, we have 6 departments: biomedical, chemical, electrical, mechanical, computing, and IT. We are in the infrastructure engineering. The reason we call infrastructure engineering is because some department called civil engineering, because we have another 2 very big group. In addition to civil, we have another 2 big group, environmental and geomatics. So that's why the name we call infrastructure engineering. In this department, we have 40 plus, 45-ish TNR academic staff. We have more than 60 research fellows. Students, we have 250-ish PhD students. The geotech group, in total, we have 7 TNR permanent tenure staff. Or offshore geotech, it's relatively new. This after Professor Mark Cassidy. He was the director of the Center for Offshore Foundation Systems at Western Australia. He moved to Melbourne in 2018, and then 1 year later, he dragged me there. So I joined Melbourne Uni in 2019. And then Associate Professor Hui Chao joined us another year later, 2020. So 3 of us very close collaboration and interest on the offshore foundations. Dr. Nagin Joseph joined a little bit later. Her background is on scoring and AI, machine learning. Well, our new staff, Dr. Schwartz Mitra, quite new now. He's replacing my teaching because I'm doing my future fellowship. So he's doing the teaching at the moment. In addition, we have another 2 postdocs at the moment, and I'm enrolling another 2 postdocs in coming months. So going to become bigger, the team. We have 24 PhD students at the moment. We have more, about 8-ish new students coming, waiting for the visas. Another 3 finished. So among these students, I'd like to highlight, we have quite a few joint PhD students. So these 2 are the joint PhD students with Toronto University, Canada here. And another 2 here with Q Leuven in Belgium. We have another 2 here with Shanghai Jiaotong University in China. So this is the team for offshore foundation, offshore geo techniques. Okay, so since we joined Melbourne, we have been developing our testing facility and numerical modeling capability. So you can see here, these traditional Traxel test facilities, and we have developed 1G testing facilities. It's a big tank, mixers, and other stuff. We use CPT, mini CPT, and this called T-bar. So this is from Macronal's Western Australia's, IP. So to penetrate the T-bar to characterize the soil. In addition, we're developing a large deformation numerical modeling technique. In the coming years, not going to be next year, maybe another 3 or 4 years later, we're going to build a new centrifuge on the new campus in Melbourne. Okay, so today I'm going to talk about helical anchor. The reason this topic is close to Professor Deng, close to your work. So we're going to give a background introduction and also show you some centrifuge testing we have done. We have done series test, but today just for a small portion of it. I'm going to show you several typical tests and talk about the effect AR on the installation on the holding capacity. Last bit is the implication for design and for installation development. Okay, the background. The offshore wind industry is booming, especially in Europe and China now. So China pretty much the biggest market now. So far, the total installed offshore wind capacity reached 83.2 gigawatts. So by last year, and also is estimated to be 380 gigawatts by 2030. So it's another big area to a big market to develop. Most of the offshore foundation is fixed foundation. All the 90% of the turbines at this moment is fixed in the seabed. Within shallow waters, less than 40 meters-ish. However, the offshore wind, 70% of offshore wind energy is in deeper water, so deeper than 60 meters. So in order to go to the deeper water, we need more economic and more technically viable solutions. Because the foundation costs for 30% of the total cost, so the big portion. So that's why we're developing new foundations. So helical anchor came to our vision. So we're thinking we're going to use this foundation for offshore wind. So what is helical pile? Helical pile, and the name, you have a shaft, you have one helix or multiple helix. And this foundation you install by give a vertical force we call crowd force compression, and also we give a torque. So basically you screw into the soil, right? It's sometimes called screw anchor, screw pile. You have large axial capacity because you have a plate here, helix here, right? And the helix here, this distance we call pitch. That's a distance, right? The opening. The reason we want to use this foundation is because it is quite installation. You just twist in, right? Twist in. For monopile, other foundation offshore, we use a huge hammer. We drop the pile down into the seabed. You make a big noise. That is the damage to the ocean mammals. In some areas, it is banned. You can't use it anymore. And also, we need heavy vessels, very expensive hammer to do that. But this one can be quicker, can be economic. This is the idea for helical pile. Helical pile is nothing new. It has been widely used onshore. Professor Deng is an expert on this perspective. So if you look at this table, the onshore helical anchor, relatively small. The diameter of your helic plate is up to 0.5 meter, right? That size. The pile length 10-ish meters, and the capacity is 300 kilonewtons. But if you go to offshore, you need much bigger upscale the foundation, right? So the challenge is, what is the mechanism and how can we install this huge helical anchors for offshore wind? So this is our challenge. Okay, so I'm going to introduce some our work, my student work on the helical anchor testing in centrifuge. So we did a lot of tests, but today I just only concentrate on the we call AI advancement ratio. So it's defined as the penetration per revolution. You twist your anchor, one revolution, one round, you have a distance, right? This distance is, let's say, divided by your pitch. The pitch is this distance. So AR equal to 1, this is traditional, we call perfect installation or pitch match installation. People thought if your AR equal to 1, you twist one revolution, you have one pitch penetration, right? So in this case, your helix go the same track. People think this have a minimal disturbance to the soil. So this is a traditional thought. So we did series test. We look at the AR effect. The AR, if AR greater than 1, you have more penetration. If AR is infinite, it becomes pure penetration like a pile without rotation. If AR smaller than 1, you have a lot of twist. AR equal to 0 means pure rotation without penetration, right? So this is the idea. And then we did series test because some tests, especially from Danny group, they did a lot of tests in sand, and they recommend overflatting AR smaller than 1. They believe AR smaller than 1, you need less cross force, and you have a greater capacity. However, in clay, this may not be true. We did test in clay. And the idea of centrifuge, I think everybody have a geotech background, don't need to introduce too much. The idea is soil is a special material, the very special material on Earth, right? So you can only add your centrifugal force, so you can increase the stress level. Thus, you can use a small model to represent the bigger one. This is the idea. So what we did, this is a typical Western Australia soil sample preparation procedure. So we use killing powder. We bought from a factory, something like that. The killing powder, people use the killing powder to make pottery and other things, very fine particle. So we mix with tap water. The water content is 190%, so double your liquid limit. So the soil is in pasty slurry, and then we mixed for a full day and vacuum with the air, no air in the pasty in the slurry. We pour in this strong box, and then we start to spin this box. When you spin the box become like this, right? The centrifugal force. We spin this at 80 G, 80 times the Earth's gravity. In this test, we spin more than 10 days for this slurry to become solid, to consolidate the soil sample. Eventually, with the T-bar, we penetrate into here. We look at undrained shell strength, the SU. You can see from the surface increasing. This is normally consolidated clay, right? The increasing with depth. Penetrate, at some step, we uplift the T-bar, and then we penetrate again to the cycles. From here, we can tell the softening of the soil sample. And this is setup. This is the strong box. We have a 2D actuator, traditional 2D actuator, you can go vertical, you can go horizontal, go here. However, for this helical pair, we need another degree of freedom, which is rotation. So we built a rotation actuator, this one. We bound this to the 2D actuator, so we can control the 3-degree freedom. You can twist and also penetrate. So this is the setup. So this is our rotation actuator. This is low cell. You can measure the torque, the vertical force. So this is the model, 80 times smaller than the real one. You can see this is helix. On top of the helix here, we put a pore pressure transducer, another one below the pore pressure transducer here and here. And we use a filter stone, cover this so you can protect it. You can measure the pore pressure during installation and uplift. So this is the test procedure. You can see this at 80 G spinning very fast. The camera sits in the box. So you can see we twist into the soil at a specified AR. And then this actuator, until we reach that, we do the uplift. During the uplift, it's locked, so no rotation anymore. You can see that when the anchor is out of the soil, there's some soil attached to the plate come out from the seabed surface. So this is a test procedure. We did both immediate uplift after installation, immediate uplift. The other one is we hold that for import type, it's 10 years. In centrifuge, several days, hold that when they allow the pore pressure to dissipate. We did both. Okay, I'm going to show you a typical test result. We change the AR all the way around from 3, 1.5, 1, 0.9, 0.75, all the way to 0.1. So a whole range of AR. I show you one test, the AR equal to 1, the perfect installation. People thought perfect installation. Okay, so this figure is a crowd force. The crowd force. We normalize, this is a very background of Western Australian style. We like to normalize, make a dimensionless factor. The way divided by area, the product area of your helix divided by the soil strength, then become a dimensionless force or factor. This is the vertical penetration. So from here, we start installation. At the beginning, 0, because the tip, we measure from here. The tip in the soil, the crowd force is very small. Until the plate part of the soil start to increase quickly, nearly linearly increase the crowd force until to your specified 4.5 times your helix diameter. That's the stop, uplift. So these two are the quick, immediate uplift. And the red one is consolidation uplift. We hold here for several days. In prototype, it's more than 10 years, and then we did uplift. You can see the uplift reducing all the way when this come out from the soil. This is not 0 because you have some soil attached to it after the output come out of the soil. We did 3 tests here. AI equal to 1, I is the immediate uplift, C is a consolidated uplift. And this one, just repeating this one, because we did 2 boxes. We want to see whether the test can be repeated or not from different boxes. So you can see we have a really great agreement. And this is easy to understand. After consolidation, you have a much greater resistance, right? This T point we call VP, which is your holding capacity of the foundation. Okay, so if you look at the torque, that's interesting. This is the torque. Again, we normalize the T by the area, SU, and another D here to make it dimensionless. Installation, torque increase until to here, and then immediate uplift or consolidated uplift, whatever. When you do the uplift, we lock the rotation. So the torque didn't reduce to 0. It has a residual value. The reason is when you lift up, the soil try to push the helix, right? They try to unscrew it because you screw in, you lift up, so try to unscrew it, which means you have to apply a force to lock that. That's the reason why it's not 0. So this is the torque. Pore pressure, this is something very interesting. We didn't expect this. So we have a top sensor, a bottom sensor of the pore pressure. When we're talking about the pore pressure, actually it's excess pore pressure. Excess pore pressure means the total pore pressure minus your static pore pressure. So initially you have a static pore pressure increasing with depth, right? But this we only talk about excess pore pressure. Okay. Installation, we look at the bottom pore pressure first. So the thick lines at the bottom one. And this one, the black one is the immediate uplift. The red one is the consolidated uplift. Installation, pore pressure increasing, positive value, which means we'll install it, the soil here is compression, right? So that is positive. When you do uplift, it becomes negative. Negative pore pressure means suction. The soil is in tension, becomes suction. And the consolidated one have a greater suction. It's easy to understand. After consolidation, soil becomes stronger. Thus, you have a greater suction. The top sensor, this is interesting. The top sensor, we thought at the beginning, when we install, the top sensor is going to be negative because when we install it, you try to separate, you have a suction, but actually it's not. You can see here, installation is still positive, which means the soil stay on the plate. It follows the plate. It didn't show a trend to separate. When you do uplift, the soil squeeze onto the plate, right? Thus, you have a greater positive pore pressure. So that's a very interesting observation. Okay, I'm going to show you the effect of AR on the crowd force. This is the crowd force. So look, we did a whole bunch of AR. The AR from 3, 0.5, 1, 0.9, 0.75, 0.5, reducing. So you can see at high AR, which is penetration dominant installation, you need great crowd force. You need press it. When the AR reducing, say crowd force reducing, right? When the AR equal to 0.9, further reduce 0.75, the crowd force become negative value, which means you don't need press it anymore. You need to hold it in order to meet your specified AR. We have this experience, right? When you install a screw, use a screwdriver onto the wall, you give at the beginning you press it, right? But some stage you only give a torque. The screw, the nail go into the wall. The reason is here, right? You don't need to press it anymore. The torque will drive into the soil. With the AR further reduced, this tension come back. The reason is at very small AR, lateral rotation, the soil disturb, soften, right? This come back. This is the reason. And if you look at the torque, at a high AR 3, you don't need much torque. Because you have a very large crowd force, you don't need much torque. With AR reducing, you need to increase your torque. You need to increase your torque. 0.5 largest torque required, right? And then further reduce the Tmax again due to softening. So this is interesting. There's no free lunch, right? You either do the draw for penetration or you do the work for rotation. So this gives some implication. I'll talk about later how to design your installation equipment. Okay, let's look at the AR effect on the pore pressure. Again, this is the bottom one. We're talking about the bottom one first. The bottom sensor pore pressure with AR reducing, AR equal to 3, you have a great pore pressure, positive one, because more compression. With AR reducing, it's become nearly 0 or a little bit suction because small AR, which means you don't penetrate much, you stay there, right? The soil try to separate. That's why you generate some sort of suction or 0 pore pressure, effect pore pressure, obviously. The top sensor here, pore pressure sensor here, this is interesting. When we do the installation, the top sensor with AR, it's great AR, you don't have much pore pressure. However, when AR reduce, you have an increasing pore pressure. The reason is when the AR is small, you don't go much, the soil have more tendency to press your sensor. We'll come back again because the softening effect. Okay, so if we look at the capacity, after capacity. So if you remember here, we install and then uplift this peak point, we call the holding capacity, right? The VP is your peak resistance. We take this VP as your capacity, we divide by the area and soil strength. We call this the capacity factor. Again, dimensionless factor. We plot this one versus the AR. You can see here, this is the immediate uplift. With AR increasing, this increasing peak at 0.9. Further increase, decrease again. This tells us 0.9, you have the minimal disturbance. So people thought 1 as a minimal disturbance, but actually it's not. It's 0.9 in this case. The reason is if you have perfect helix, by saying perfect, I mean the helix have no thickness and it's perfect smooth. In this case, 1 gonna be the perfect installation, but the actual helix is not. It's always have roughness, have a thickness, right? So you cause disturbance to the soil. Thus, in this case, 0.9 is an optimal capacity. So this is the immediate capacity. For the consolidated capacity, with AR increasing this increase, easy to understand, great AR penetration dominated great capacity. Okay. We then plot the pore pressure, the peak pore pressure, the top sensor pressure positive, the bottom pore pressure suction for immediate uplift, consolidated uplift. You can see after consolidation, the top sensor pore pressure reduced a little bit, but the bottom one increased, and the thing increased, the suction increased a lot, right? So you can the distance from this line to this line, the red line from this line to this line, the distance is the pore pressure force acting on this plate. So we plot this one, the pore pressure difference versus the capacity, the total capacity. So this 1-to-1 line and this line is 85%, which means the helix contributed 85% of your capacity. The other 15% is from the shaft. This is for immediate uplift. For consolidated uplift, the plate contributed 70%, and the shaft contributed 30%. And then we look into the torque factor we call KT or KT star. KT star is the empirical parameter. People use it to estimate your uplift capacity from your installation torque. So because we have the full data here, we can back calculate KT star by using the capacity divided by your torque. So we have this line, the immediate uplift, the consolidated uplift, these are the factors. At small AR, this is low, the radius. At small AR, you need big torque. Your capacity is small. But at greater AR, you don't need much torque. Your capacity is great, right? So that's the reason. Look at this. We compare with other empirical parameters in the literature. Okay, I think I'll go to probably the last bit is on the installation equipment. This is the challenge for us. Professor Deng also talking about this. So for onshore, you have an excavator or bobcat. You just make the hydraulic motor to install, give a torque to install. But for offshore, we need a much bigger plant or installation equipment. How do we do that? Especially you have a barge on the ship, right? You have a great torque. How do you resist your ship movement, right? So we try to improve our confidence on this. So we draw the installation into this figure, the cross force, weight, and the torque. For great AR, you need a great cross force, but less torque. With the AR reducing, you need a great torque. You don't need a much cross force at all, or even tension, right? So again, you can either do penetration-dominated installation by using a great vertical force. Alternatively, you can do a torque-dominant installation by applying a big torque where you don't need a much cross force. You can do both. For example, here, this helical anchor helical paddle, the shaft 0.8 meters diameter, the helix 2.6 meters in diameter, the penetration 11 meters. For this anchor, the torque for this two extreme case is the required torque is 40 kilonewton meter and 96 kilonewton meter for this one and that one. And the rotation power, the motor power is 45 kilowatts, 107 kilowatts, amounts to 60 and 143 horsepower. If you want to install by using two different modes. The required cross force for this one is 650 kilonewton, 65 tons to install this. So the application for engineers is you can use this. I mean, different from sand. This may be used. You can use a cross force by using dead weight. You have a lift, right? You lift up with dead weight. You don't need much torque at all. So it can be an option. Okay, I think I just stop here. And last, I'd like to acknowledge the support from Australian government, including my future fellowship from ARC Council, we call Australian Research Council. And the other one is several discovery products. We also have discovery products lead by me. And recently we got a CRCT working with industry on the offshore wind turbine foundation system in Australia. This work is mainly from my student, Zeliang, his work, and also private students, my postdocs, together with my colleague and former colleagues. Last but not least, I'd like to thank Professor Deng and you guys for your hospitality and hosting here. Great pleasure to give this talk. Thank you all.
So like if anyone of you over here or online have any sort of queries for Professor Tian, please ask. And for over here audience, like please raise your hand so that we can like hand over you the mic. Jerry, like will you be able to with mic? We have one raised hand.
This one, right?
Very nice. Hello. Hi, thank you for the presentation, Dr. Tian. So right now we are looking at the normally consolidated soil and installing the helical pile. How do you think the behavior will be different for an over-consolidated soil, like the marine are usually over-consolidated? Secondly, in offshore geotechnics, like the effect of earthquake or the tsunami waves, like how can they change the AR effect or the pore pressure development? Like it will be more different, or you think it will be same? Thank you.
Thank you. Very good question. In this test, we only concentrate on normal controlled soil. For all controlled soil, we didn't do much work yet. My understanding is the behavior should be similar as long as undrained. The trend should be similar, but the force can be different. All controlled can be much stronger, can be much harder to install. This is probably your first question, but behavior can be still undrained. The second one is the earthquake and other questions, right? Earthquake. We didn't consider earthquake. Actually, in my research, I never done any work related to earthquake because in Australia it's not a big problem. Not sure earthquakes is important in Canada or not. There are some earthquake zones, right? So I don't know. So the question I don't know. For some soil can be critical because it can cause liquefaction, can cause problem. But for us, for this clay soil, I don't know. For silty soil can be critical because liquefaction can happen, right? But for this one, hard to say. Yeah.
So the AR effect, like, is it?
Okay. Yeah.
Can you say like it is the strain rate? Like, do we have a strain rate for like how it is going on? Like,
Yeah. For the AR, in this test, because the AR is a ratio, right? But you have an absolute speed or velocity. We designed the velocity such that it's within undrained condition, so pretty quick. So that's one. The other thing I want to say is this is a laboratory condition. We can precisely control whatever we want. This is the first step. But in reality, I don't think you're going to control AR. Pretty much you can use load control. You give a dead weight, low weight. The AR may free to change whatever you change. Actually, we did some work on that. We use a load control. We give a constant load, and we look at the AR. The AR we've got something interesting, but today I didn't got time to talk about this. Yeah.
Do we have any other questions?
Is there one other question?
Yeah, one online.
No.
Yeah, okay.
So this is Tian.
Yep. Okay. Yeah.
Okay, thank you, Professor Tian. That's very nice talk, and then you really shed the light on our, simple modeling technique with our Canadian colleagues and students. I really appreciate it. Yeah, I guess most of us, we came from overseas, right? And maybe Canadian as well, but never seen ocean. Most of us, right? And never play with any offshore soil, honestly, right? Except for me, perhaps. But I I put my hand dirty in the offshore soil in Western Australia. I know that, but I guess now as otherwise nobody knows about what offshore soil look like in maybe in the Western Australia coast, right?
Yeah.
So and then that bring up some questions about the global consolidation and stress history and that kind of questions. Like, so maybe can you elaborate, what kind of offshore soil you are can simulate perhaps right from the Western Australia, right? And then do you often see over consolidation? Like what kind of particle size you're looking for? Maybe for the prototype soil, right? Prototype Western Australia, and cohesive, or the carbonate, maybe give some very high level.
Thank you. Thank you, Professor Deng. You are the expert on helical. Yeah. So yes, so offshore, we do have our consolidated soil, especially in North Europe, Norway, because history, like iceberg glacial activity, the soil can be very over-consolidated as soil. In Australia, we don't have much that case. Australia soil, if you go deep water, becomes silty, clay soil. But when you near to shore, especially in Western Australia, and also Melbourne, Victoria, we call Bass Strait, next to Tasmania, that bit is quite carbonate, the Kepler sand, Kepler silt soil. So this work is our first step to carry out this research project. So we start from something simple. We didn't use the real soil. I think it's real soil. We didn't use the practical soil. We use killing powder. Killing powder we use a lot in Western Australia because it's consistent. The property we know well. We have done this so many years. Everything is quite confident. This is the reason why we use killing powder.
The other question we're having is that, right, so these anchors, they're not very deep, right? The depth ratio, if we look at that, is only about 4.
4, yeah.
So is that because limitation of the experiments or just
limitation for strong box? So for this test, we think, okay, we just use the small centrifuge. We have 3 centrifuge back in UWA. So 2 beams, 1 drum. Then we use the small C60, the small one. We didn't use the big one. The big one is super hard to use, not to challenge it. We use the small one. So we say, oh, we stop there. We cannot do too big, too deep foundation. But enough for us to investigate the mechanism.
Perfect. Thanks so much.
Thank you.
Thank you, Professor Tian. I just had a small question. So for the centrifuge, when you did the test for the helical piles, do you have any sort of load cells or a strip just to measure if there is any possible boundary effect to the helical pile that is coming during the installation and the loading? Can you really tell?
My understanding, you ask what sensor load cells we use on the foundation or to eliminate boundary conditions?
Yes.
That's a good question. We don't. I think I never did that. Not that. But maybe it's an empirical occurrence. Normally, we have a distance like 40, 5D-ish from experience to the wall to avoid to avoid boundary effect.
Okay.
Yeah. But we never put sensor to do that.
Yeah, and we tried for one time, probably with one of our centers, but we're having some issues with that. But we have some loud noises in it. Yeah.
Depend on your foundation or what you are doing, right?
Yes.
But this one is relatively okay because the helical pile, you don't have much disturbance. Okay. They just screw in and pretty much 1D is enough, 1D, 2D enough.
Thank you so much.
very much for the presentation and the Tian. I just wanted to ask, when I was looking at the figure of your helical anchors, is there any advantage between having multiple helical anchors and just a single? Then, secondly, when you're changing your AI, was there any difference bigger mechanism of soil?
Yeah. Okay, thank you. Very good question. I didn't show, actually, we did some work by use 1 helix, 2 and 3 helices. Very interesting. Today I just asked Professor Deng the auger, more like screw anchor on that one. So we found very interesting. If you add a multiple helix, you do increase the capacity, but not that much. You think you use 2 helices, the capacity never gonna double. The reason is you have a bottom one, you have a top one. Let's say same size, okay, same diameter. If the top one close to the bottom one, they are too close, you don't increase much at all. But once you have enough distance, you get an improvement. But once this distance too big, your top one going to be shallow. The contribution reduced again. So this is more like in a team, the best position is everybody contribute, right? Rather than influence each other. There's something interesting we saw. This you have to have enough clearance such that everybody work independently, but not too far away, right? You still want to, the second one keep deep. That's probably your first question. What's the second one? Sorry, the second question is on the mechanism about that. Yeah, the feedback. Yes. Different AR have a different feedback mechanism. We can see, and also they have influence on the capacity. So high AR is more like the soil flow around, more like traditional flow around. But small AR is more disturbance of your soil, and also the capacity is different. High AR have a higher capacity as consolidation.
Do we have any other questions? Okay, so we also have got a small souvenir for Dr. Tian. I would like to invite Dr. Lee Zhongden, our Professor Lee Zhongden, to hand over the souvenir. And Zero, please help.
Thank you.
All right, so
Thank you so much.
On behalf of us, Geotech Group,
Okay,
we're
thank
really
you.
pleased to have you.
Oh, thank you so much.
Okay.